So last video, we introduced what are vectors and did a little bit of notation for vectors here as well. But the explanation I gave us maybe a little bit hand-wavy. It wasn't really too precise. We want to be able to do things a little bit more precisely here. And so the thing that I want to go back to is this picture where we have these four equal vectors here. These are all equal. Well, one of the vectors is in some ways nicer than the other vectors. And the one that's the nicest is the one with initial point is the origin. And so here's a fun little fact, is that any vector that we draw, like this one, okay, so let's say this is going from P to Q, we can pick this up and translate it without changing its direction or its length so that its initial point is at the origin. And so what we're going to do is that doing this process is called moving a vector to standard position. And the idea is that like all vectors, we're going to kind of think of as being, if they're not in standard position, we're going to kind of think of them as being in standard position. So so this kind of leads us to our, this was our previous definition of like what vectors were here. This is going to be our much more computational way that we're going to be able to represent vectors here. So if V is and I've written this out twice we can have vectors either in 2 dimensions or 3 dimensions. It really works in the same way that, when I said in the last video I drove 150 miles southwest, that's, for our intents and purposes, that's kind of moving in 2 dimensions, but, north, south, east, and west. But, if we were in a rocket, we might, going up into space or something like that, flying an airplane, we're moving in 3 dimensions. So V is a 2-dimensional vector in the plane equal to the vector with initial point 0, 0, moving it to standard position, and terminal point V1, V2. We can write V in component form as vector V is equal to left bracket, V1, V2, right bracket, where it's these sharp brackets. So not this kind of bracket, not open parentheses. Open parentheses we use for points here. We want these sharp brackets to represent vectors. And then similarly, and V is a 3-dimensional vector in space. Sorry for all of the typos here. In space, equal to the vector with initial point 0, 0, 0, the origin, once again, and the terminal point V1, V2, V3. Then the component form of V is vector V is equal to, these sharp brackets, V1, V2, V3. Okay, so this is how we're going to think about vectors here. So let's maybe at this point, let's do one more definition here about magnitude and length here. So the magnitude or length of a vector, V is equal to PQ. I'm doing this in 3 dimensions. I'm doing this in 3 dimensions, but this also works in 2 dimensions as well. Just chop out the last part. The magnitude of V, the length of V is just given by, just do the 3-dimensional, this should look just like the 3-dimensional distance formula. So you take the component, so up here, you take the components of V and you square each component and you sum up the squares. And if we're thinking of this going from P, point P is corresponding to x1, y1, z1, q is corresponding to x2, y2, z2. It's just the 3-dimensional distance formula from point x1, y1, z1 to x2, y2, z2. By the way, little asterisk down here, magnitude or length, we use those two terms interchangeably in this course. If you take other courses like linear algebra, sometimes you'll see the word norm get used for the length of a vector. And so I'll try to only use magnitude and length, and I'll use those two terms interchangeably. I'll try to avoid using the term norm, but if you see in other classes or just people are talking about and they say norm, that just means the length of your vector, the magnitude of the vector. Okay, so let's do an example of this here. So find the component form and length of the vector with initial point P is -3, 4, 1, terminal point Q, -5, 2, 2. So how do we do this? So to form our vector, let's say vector V is the vector from P to Q. I guess maybe I should have written this out as a separate slide, but just definition by example, how do we get components here? So we're going from P to Q. So we do the first entry here, the x coordinate of Q, minus the x coordinate of P. And then we do the y coordinate of Q, minus the y coordinate of P, and we do the z coordinate of Q minus the z coordinate of P. Doing the arithmetic here, -5 minus 3 will be -2. 2 minus 4 is -2, 2 minus 1 is +1. So this right here, this is the component form of the vector that's going from, so -3, 4, 1 to Q here is -5, 2, 2. So this vector has components -2, -2, and 1. To find the length of V, the length of this, all we have to do is sum up the squares of the components and then take the square root. So the magnitude of V is the square root of -2 squared plus -2 squared plus 1 squared. -2 squared is 4, -2 squared is 4 plus 1. That sums to 9. Square root of 9 is 3. So 3 is the magnitude, 3 is the length of this vector. 3 is also the distance from -3, 4, 1 to -5, 2, 2 using the three-dimensional distance formula from last class. Okay, so this shows how to compute magnitudes, lengths. This shows how to compute component forms of vectors. So let me just then revisit. Let me just end this video a couple of a little bit of revisiting a previous thing and another definition or two. Two vectors are equal if they have the same length and direction. So now we can say two vectors are equal if they have the same components. And so in this case, let me just do a 2D example. So suppose here that this point is the point 1, 3, and we want to draw, this is the point 2, 1. And then let me draw over here the point 5, 2, and then the point on the axis here, 6, 0. Suppose that this is vector u, and this is vector w here. The components of u, the components are u, 2 minus 1, and 1 minus 3, which is going to be 1, -2. And the components of W are going to be 6 minus 5 is 6 minus 5 is going to equal 1, and 0 minus 2, which is negative 2, and these two things are equal, and so we say here that vector u and vector v are W. They are both equal to the same vector in standard position, and that's this vector here, which goes from 0, 0 to 1, negative 2 here. So these three vectors, I mean, they don't quite look parallel. That's just because I'm not drawing it perfectly. They're supposed to be parallel. These three vectors are all equal. They're equal if their components are equal. One last thing to do in this video, and just to squeeze it in here, has to do with a special vector, the 0 vector. So the 0 vector is the vector with components. Every single component here is 0. This is the 0 vector in 3 dimensions. You can also have a 0 vector in 2 dimensions, just have 2 components. You know, we're more interested in the 0 vector in 3 dimensions. And the way that we represent the 0 vector is with 0, but with a vector sign over it. And so, you know, in the last video I said, you know, it's very recommended that you put, little half arrow hats on top of your U's and V's and W's to make it clear that they're vectors. You know, it's really pretty close to mandatory. You know, 0, the number, and 0, the vector, these are not the same objects. This is a number. This is a vector. This is really 3 zeros. You know, there will be a special term that we're about to learn about scalars. Scalars are really just real numbers. You know, please be able to, you know, let me just end the video with this in all caps. Please learn to distinguish between vectors and scalars. So, all throughout this class, some of your answers to problems are going to be vectors. Some of your answers to problems are going to be scalars. If you don't know what form of an answer you're supposed to get, it's going to make solving the problem a lot more difficult. So please be able to distinguish not just between 0, the number, and 0, the 0 vector, but more generally between all vectors and all scalars.